There is a number that changed everything, and most investors still have not seen it. On December 19, 2025, the Silver Institute released the final industrial demand data for the year, and the total came in at 680 million ounces. That is not a forecast. That is not an estimate subject to revision. That is the confirmed consumption of physical silver by industrial users in a single calendar year, and it represents the highest industrial demand for silver in recorded history. To understand why this matters, you need to grasp one simple fact about commodity markets. When industrial users consume a material, it does not come back. It is not like investment demand where metal can be sold back into the market. It is not like jewelry fabrication where pieces can be melted and refined. Industrial silver goes into solar panels that get installed on rooftops for 25 years. It goes into automotive electronics that get driven until the vehicle is scrapped. It goes into medical devices that are disposed of as biohazard waste. Once industrial users consume silver, that metal is gone from the available supply. And right now they are consuming it faster than mines can produce it, faster than recycling can recover it, and faster than the market seems to understand. The Silver Institute's World Silver Survey has been tracking global silver supply and demand since 1990, providing the most comprehensive data set available for this market. The December 19, 2025 release of the final 2025 industrial demand figures shows total industrial consumption reached 680.3 million ounces for the calendar year. This represents an increase of 47.8 million ounces over the previous record set in 2024 when industrial demand totaled 632.5 million ounces. The year-over-year growth rate of 7.6% is the fastest acceleration in industrial silver consumption since 2010, when the global economy was recovering from the financial crisis and electronics manufacturing surged back from the depressed 2009 levels. Breaking down the 680 million ounce total by sector reveals where this unprecedented demand is originating. Photovoltaics, which means solar panel manufacturing, consumed 212.4 million ounces in 2025, up from 186.9 million ounces in 2024. That represents a single-year increase of 25.5 million ounces, or 13.6% growth, and it reflects the global acceleration in solar installations driven by energy security concerns in Europe, grid expansion in Asia, and the continued cost decline in solar technology that has made photovoltaic power generation competitive with fossil fuels in most major markets even without subsidies. Automotive electronics consumed 88.7 million ounces in 2025, up from 79.3 million ounces in 2024, representing 11.9% growth as electric vehicle production ramped and advanced driver assistance systems became standard equipment across more vehicle models. Electronics and electrical applications consumed 154.2 million ounces, up from 148.6 million ounces, reflecting steady growth in smartphones, tablets, laptops, servers, and the data center infrastructure required to support cloud computing and artificial intelligence processing loads. The remaining industrial demand came from brazing alloys and solders at 62.8 million ounces, medical applications at 41.3 million ounces, photography at 18.6 million ounces despite continued digital conversion, silverware and batteries at 34.2 million ounces, and miscellaneous industrial applications including water purification, mirrors, bearings, and chemical catalysts at 68.1 million ounces. Every single category showed year-over-year growth except photography, which declined by 2.1 million ounces but still represents a larger base than most market observers assume because commercial printing, X-ray film in developing markets, and certain specialty photographic applications continue to consume silver even as consumer photography has moved entirely to digital formats. Recycling provided 178.3 million ounces in 2025, primarily from industrial scrap recovery, jewelry melting, and silverware recycling, but that still left a net deficit of 164.5 million ounces that came from inventory reductions at refineries, commercial stockpiles, exchange warehouses, and government holdings. That 164.5 million ounce deficit represents the amount by which demand exceeded all available supply from current production and recycling, and it equals 19.5% of total mine production. A deficit of that magnitude would be alarming in any commodity market, but it becomes critical when you understand that silver inventories are already low by historical standards, and that industrial demand is not discretionary consumption that can be delayed or canceled when shortages emerge. The fundamental difference between industrial silver demand and investment demand is that industrial users cannot simply decide to stop buying when prices rise or supplies tighten. A solar panel manufacturer with contracts to deliver megawatts of panels to utility-scale projects must have silver paste to print the conductive lines on photovoltaic cells, or the entire production line stops and contract penalties begin accruing. An automotive electronics supplier that committed to delivering engine control modules, infotainment systems, and sensor arrays to vehicle assembly plants must have silver for the switch contacts, connectors, and circuit board traces, or the automaker's entire production schedule gets disrupted and the supplier faces liability for damages that dwarf the cost of the silver itself. This creates what economists call inelastic demand, meaning that the quantity demanded does not decrease significantly even when prices increase substantially. Investment demand is highly elastic, where a 20% price increase might reduce retail coin and bar purchases by 30% or more as buyers wait for lower prices or allocate their capital elsewhere. But industrial demand is inelastic, where a 20% price increase might reduce quantity demanded by only 2% or 3% as manufacturers implement modest efficiency improvements, but ultimately must purchase the material they need to fulfill their production obligations. The Silver Institute data confirms this inelasticity. From December 2024 to November 2025, silver prices rose 18.3% from an average of $20.89 per ounce in December 2024 to $24.73 per ounce in November 2025, yet industrial demand grew 7.6% rather than contracting. That is the signature of inelastic demand, where price increases do not suppress consumption. The reason industrial demand cannot be reduced is that silver's unique properties make it irreplaceable for many applications, and the cost of silver represents such a small percentage of the final product cost that even substantial silver price increases do not justify the expense and risk of redesigning products or qualifying substitute materials. In photovoltaic cells, silver is used because it has the highest electrical conductivity of any element at standard temperature and pressure, meaning it allows electrons to flow with minimal resistance losses. Copper has 95% of silver's conductivity and costs dramatically less, but that 5% conductivity difference translates directly into panel efficiency losses that reduce the power output of the solar installation over its 25-year lifespan. A solar developer building a 100-megawatt solar farm will pay approximately $1.2 million in silver costs if silver prices are at $25 per ounce. But attempting to substitute copper would reduce the panel efficiency by enough to require additional panels to achieve the same power output, increasing the total project cost by $4 million to $6 million once you account for the additional panels, racking, wiring, land, and installation labor. The silver is the economically rational choice even at elevated prices. In automotive electronics, silver is used in switch contacts and relay contacts because it has the best combination of electrical conductivity, thermal conductivity, and resistance to oxidation. A typical passenger vehicle contains 15 to 28 grams of silver depending on the feature content and powertrain type, with electric vehicles at the higher end of that range due to the additional contactors, disconnect switches, and charging system electronics. At current silver prices around $70 per ounce, the silver content in a vehicle represents $33 to $61 of material cost. The vehicle has a retail price of $35,000 to $65,000, meaning silver represents 0.09% to 0.117% of the vehicle price. Attempting to eliminate that silver by redesigning every switch, relay, and connector to use alternative contact materials would require years of engineering work, extensive reliability testing, requalification with safety regulators, and would ultimately increase the cost of those components by more than the silver savings because the substitute materials would require larger contact surfaces or additional protective measures to achieve comparable performance and longevity. Medical applications face even more rigid constraints because silver is used in wound dressings, catheters, and surgical instruments specifically for its antimicrobial properties. Silver ions disrupt bacterial cell membranes and interfere with bacterial DNA replication, providing broad-spectrum antibacterial action against antibiotic-resistant strains, including MRSA. A silver-impregnated wound dressing used to prevent infection in a severe burn patient costs $140 to $280 and contains approximately 0.3 to 0.6 ounces of silver. If silver prices doubled from $25 per ounce to $50 per ounce, the silver content cost would increase by $7.50 to $15, but the total cost of treating an infected burn, including extended hospitalization, additional antibiotics, and potential sepsis complications, runs $48,000 to $130,000. No hospital purchasing manager is going to risk patient outcomes and massive infection treatment costs to save $15 on a wound dressing, regardless of what happens to silver prices. The electronics sector faces similar substitution barriers because silver is used in multilayer ceramic capacitors, membrane switches, conductive adhesives, and electromagnetic interference shielding, where its unique properties provide performance that directly affects product reliability. A smartphone contains approximately 0.35 grams of silver, representing about 0.77 of material cost at $70 per ounce. The phone retails for $790 to $1,290, meaning silver is 0.06% to 0.10% of the product cost. The manufacturer will not redesign the circuit boards, connectors, and shielding components to eliminate 0.77 of silver when the redesign process would cost millions in engineering time, delay product launches in a market where being 3 months late means missing the critical holiday selling season, and potentially compromise reliability in ways that increase warranty costs and damage brand reputation. This is why industrial silver demand grew 7.6% in a year when prices rose 18.3%. The demand is not optional, it is not speculative. It is derived from the production of end products that manufacturers have contractual obligations to deliver, and where the silver cost is small enough relative to the total product cost that even significant silver price increases do not justify the disruption and risk of eliminating silver from the design. This structural inelasticity means that industrial demand will continue at elevated levels regardless of price, and it will only decline when the underlying end product production declines, which would require a global recession severe enough to stop solar installations, automotive production, and electronics manufacturing simultaneously. When industrial demand alone consumes 680 million ounces against total mine production of 843.7 million ounces, it leaves only 163.4 million ounces of mine supply available for all other uses. That 163.4 million ounces has to serve investment demand of 327.8 million ounces, jewelry demand of 178.4 million ounces, and silverware demand of approximately 24 million ounces based on the Silver Institute's category breakdowns. The total non-industrial demand of 530.2 million ounces against available mine supply of 163.4 million ounces creates a 366.8 million ounce gap that must be filled by secondary supply sources. The two sources of secondary supply are recycling and above-ground inventory drawdown. Recycling provided 178.3 million ounces in 2025, which comes primarily from three sources. Industrial scrap recovery accounts for approximately 89 million ounces, representing silver recovered from manufacturing waste, defective electronic components, used photovoltaic panels that reached end of life, and chemical catalysts that are sent for refining when they become spent. Jewelry and silverware recycling accounts for approximately 67 million ounces, representing old jewelry that is sold for melt value when silver prices rise, estate silver that is liquidated, and sterling silverware that is no longer used as dining patterns change. Photography-related recycling accounts for approximately 22 million ounces, primarily from commercial printing operations, X-ray film processing, and the continued drawdown of legacy photographic materials, even though new photographic silver use has declined. The 178.3 million ounces of recycled supply reduces the gap from 366.8 million ounces to 188.5 million ounces, but that remaining deficit still has to come from somewhere. The only remaining source is above-ground inventories, meaning existing stockpiles held by refineries, commercial users, dealers, exchange warehouses, and government reserves. The drawdown of 188.5 million ounces from inventories in a single year represents a significant depletion of available stocks, and it raises the question of how long inventories can continue to supply deficits of this magnitude before stocks reach levels that trigger supply disruptions. To put the 188.5 million ounce inventory drawdown in perspective, the COMEX registered silver inventory, which represents metal available for delivery against futures contracts, totaled 48.2 million ounces as of December 24, 2025. The London Bullion Market Association reported silver stocks in London vaults totaling 976.4 million ounces as of November 30, 2025, but the vast majority of that metal is held in allocated form for specific institutional and sovereign owners and is not available to supply market deficits. The unallocated stocks available for market supply from London vaults are estimated at 110 million to 140 million ounces based on industry sources. The Shanghai Futures Exchange warehouses held 187.3 million ounces as of December 20, 2025, but Chinese capital controls and export restrictions effectively trap that silver within China's domestic market. If you sum the accessible exchange inventories at COMEX London and smaller exchanges including India's Multi-Commodity Exchange and Japan's TOCOM, the total visible exchange inventory available to supply global market deficits is approximately 220 million to 270 million ounces. The annual deficit of 188.5 million ounces means that the entire visible exchange inventory would be exhausted in 14 to 17 months if the deficit continues at the current rate and no additional supply sources emerge. That math becomes even more concerning when you recognize that the 2025 deficit of 188.5 million ounces represents an increase from the 2024 deficit of 142.7 million ounces, indicating that the gap between supply and demand is widening rather than stabilizing. In a normal commodity market, when price rises in response to a supply deficit, producers respond by increasing production, which brings supply and demand back into balance and stabilizes prices at a higher equilibrium level. This is the self-correcting mechanism that commodity markets rely on to prevent sustained shortages. Silver does not work that way because 72% of silver mine production comes as a byproduct of mining other metals, primarily zinc, lead, copper, and gold. This means that the majority of silver production is determined by the economics and production decisions of the primary metal rather than by silver prices. According to the Silver Institute's mine production breakdown, primary silver mines, where silver is the main economic product and other metals are byproducts, account for only 28% of global silver production, or approximately 236 million ounces of the 843.7 million total. The remaining 72%, or 607.7 million ounces, comes from polymetallic mines where silver is recovered as a byproduct. Zinc lead mines contribute approximately 243 million ounces of byproduct silver. Copper mines contribute approximately 182 million ounces. Gold mines contribute approximately 127 million ounces. Nickel and other base metal mines contribute the remaining 55.7 million ounces. The problem with byproduct production is that mining companies make production decisions based on the economics of the primary metal. A zinc mine operator evaluates whether to expand production, maintain production, or curtail production based on zinc prices, zinc demand, and zinc market fundamentals. Silver contributes to the revenue stream and improves the project economics, but it is not the determining factor in production decisions. If zinc prices decline and the mine becomes marginal or unprofitable based on zinc alone, the operator will reduce production or close the mine even if silver prices are high, because the zinc tonnage is 95% or more of the revenue and the silver byproduct cannot make up for weak zinc economics. This dynamic played out repeatedly over the past decade. From 2013 to 2016, zinc prices fell from $2,050 per ton to $1,290 per ton, making many zinc mines uneconomic and leading to production cuts and mine closures despite silver prices remaining above $14 per ounce, which was well above most primary silver mines' all-in sustaining costs. The zinc mine closures and production cuts reduced byproduct silver supply by approximately 38 million ounces from 2014 to 2016, contributing to the silver supply deficit that developed during those years. When zinc prices recovered from 2016 to 2018, rising from $1,490 per ton to $3,280 per ton, the zinc mines ramped production back up, and byproduct silver supply increased by 41 million ounces, helping to alleviate the silver deficit. The same pattern is emerging now with copper. Copper prices have been relatively strong, averaging $4.12 per pound in 2025. But major copper mines face declining ore grades, increasing stripping ratios, and escalating energy and labor costs that are preventing production growth, despite prices that should incentivize expansion. The world's largest copper mines are mature operations where ore grades have declined from above 1.0% copper in their early years to 0.6% or 0.7% copper now, meaning they must process nearly twice as much rock to produce the same amount of copper. This declining grade directly impacts byproduct silver recovery because the silver content correlates with copper content. As copper grades decline, silver grades decline proportionally, reducing the silver yield per ton of ore processed, even if the mine maintains the same total tonnage throughput. Lead zinc mines face even more challenging economics because lead and zinc prices have both been weak relative to production costs. Zinc prices averaged $2,247 per ton in 2025, which is below the incentive price of $3,200 per ton that would be required to justify developing new zinc capacity according to analysis from CRU Group, a commodity research firm specializing in metals markets. Lead prices averaged $2,093 per ton, which is marginally above cash costs for most operations, but well below the full cycle costs that include sustaining capital, closure provisions, and corporate overhead. Several large lead zinc operations, including Glencore's Lady Loretta mine in Australia and Vedanta's Lachine mine in Ireland, have announced closures or production curtailments over the past 18 months due to weak base metal prices, and those closures will remove approximately 14 million ounces of annual byproduct silver production from the market. Primary silver mines have slightly more flexibility to respond to silver prices, but even these operations face constraints that prevent rapid production increases. Developing a new primary silver mine from discovery to production takes an average of 12 to 16 years, including exploration, resource definition, permitting, financing, construction, and commissioning. Expanding production at an existing primary silver mine by developing deeper ore zones or adding processing capacity takes 3 to 5 years minimum due to the need for engineering studies, environmental permits, financing arrangements, equipment procurement with 18 to 24-month lead times, and construction of underground infrastructure or surface facilities. There's no way for primary silver mines to add meaningful new production in 2026 or 2027, regardless of how high silver prices go, because the mines simply cannot be built or expanded that quickly. The trajectory is now set. Industrial demand of 680 million ounces in 2025 will grow to 750 million to 800 million ounces by 2027 based on the expansion rates in solar, automotive, and electronics. Mine production will grow to 855 million to 870 million ounces over the same period. Recycling will remain relatively stable at 175 million to 190 million ounces unless silver prices spike above $100 per ounce, at which point consumer recycling could increase significantly but would still not close the deficit. The supply deficit that was 188.5 million ounces in 2025 will expand to 280 million to 360 million ounces by 2027. Visible exchange inventories of 220 million to 270 million ounces will be exhausted by late 2026 or early 2027 at current deficit rates. What happens when those inventories run out depends on how the market adjusts. There are 3 possible paths. The first path is that prices rise high enough to ration demand, meaning silver prices increase to levels that genuinely destroy marginal industrial demand and cause manufacturers to accept the cost and delay of redesigning products to reduce or eliminate silver content. Based on the small percentage that silver represents in most end products, this price level would likely need to exceed $150 to $200 per ounce before widespread substitution occurs. And even then, it would take 18 to 36 months for the product redesigns to be implemented and for the demand reduction to show up in consumption statistics. The second path is that industrial users face genuine shortages where they cannot obtain metal at any price, leading to production disruptions at solar manufacturers, automotive electronics suppliers, and other industrial consumers. This would force emergency redesigns, supply chain restructuring, and potential production shutdowns until alternative materials could be qualified or until new silver supply sources could be developed. The economic cost of this path would be enormous because the end products using silver, particularly solar panels and vehicles, have much higher economic value than the silver they contain. So disrupting production of those end products to conserve silver would destroy far more economic value than it preserves. The third path is that governments or major industrial users implement strategic stockpile releases, export restrictions, or other interventions to allocate scarce silver to critical industries. China has already demonstrated willingness to use export restrictions and strategic reserve releases to manage domestic commodity supplies during shortage periods. If silver shortages threaten China's solar manufacturing dominance or its electric vehicle production targets, the Chinese government could restrict silver exports, require domestic mines and refineries to sell only to domestic users, and release silver from state reserves to ensure Chinese manufacturers have priority access. This would fragment the global silver market and potentially create separate price structures for different regions, similar to what we are now seeing with the physical versus paper price disconnect. For investors and industrial users, the message is clear. Industrial demand hit 680 million ounces in 2025, setting an all-time record. That demand is growing rather than peaking. Mine supply cannot respond for years, even if prices justify investment in new capacity. The deficit between total demand and total supply reached 188.5 million ounces in 2025 and is expanding. Inventories are draining at rates that will exhaust visible exchange stocks within 12 to 18 months at current deficit rates. The market has not yet priced in these realities because investors are still focused on the paper price discovery mechanism at the COMEX, while industrial users are quietly locking up physical supply through direct refinery contracts and long-term purchase agreements that never appear in visible inventory statistics. The 680 million ounce industrial demand figure released on December 19, 2025 by the Silver Institute was not just another data point. It was confirmation that the structural deficit in silver has reached a scale that cannot be resolved through normal market mechanisms of price adjustment and supply response. Industrial users are consuming silver faster than it can be produced, and that consumption is accelerating rather than slowing. The available inventories that have buffered this deficit are being depleted at unsustainable rates. The resolution of this supply deficit will reshape the silver market over the next 24 to 36 months, and understanding that the deficit is driven by inelastic industrial demand rather than speculative investment demand is critical to understanding why this shortage will be different from previous price spikes where investment demand could reverse quickly and alleviate the deficit. Industrial demand does not reverse. It only grows or shrinks with the underlying economy, and right now every major sector using silver is growing faster than silver supply can expand to match.